Hello students, let us discuss the chemical properties of group 18 elements, that is noble gases. Before discussing the chemical properties, let us just look into the physical properties. All the noble gases are monoatomic. Why? Because they have no combining capacity because of the stable configuration. Therefore, they exist in the nature as monoatomic form. They are colorless, odorless and tasteless. They are sparingly soluble in water. They have low melting point and boiling point because the only type of interatomic interaction in these elements is the weak dispersion force. It's quite important point here. Why these have low melting point and boiling point? Because of the weak dispersion force. Therefore, it have low melting point and boiling point. Next, helium has the lowest boiling point, that is 4.2 Kelvin of any of the known substance. So, from all the known substances, helium is a substance which have the lowest boiling point, that is 4.2 Kelvin. So, these are the important physical properties of group 18 elements. Now, let us discuss the chemical properties. In general, noble gases are the least reactive. Why? Because of some reasons. So, let us look into the reason. The first reason, except helium, all have completely filled the ns2np6 electronic configuration in their valence shell. That is known to you. In the helium, only single shell is there. That is the first shell in which maximum 2 electron can be accommodated. So, except helium, other all elements in this group having ns2np6 configuration, that is in the valence shell. So, that is a stable configuration. Because of the stable configuration, they usually not combine with other elements. We can say that its combining capacity is nearly 0. So, because of the stable configuration. And they have high ionization enthalpy because of their stable configuration. They does not lose the electron. They neither lose the electron or nor gain the electron. So, because of this reason, they have high ionization enthalpy and also they have positive electron gain enthalpy because they have no tendency to accept the electron because of its stable configuration. So, we can say that they are least reactive because of the two reasons. That is, the most important reason, they have a stable configuration. And because of the stable configuration, they have high ionization enthalpy and they have more positive electron gain enthalpy. But still they show some reactivity. That is, number of xenon compounds mainly with most electronegative elements like fluorine and oxygen have been synthesized. As I told you, even though it is the least reactive because of its stable configuration, but still it is able to generate or synthesize some compounds of xenon. Xenon is a member of group 18. That compound is usually made with the most electronegative element like fluorine and oxygen. So that is most important question here. Why the fluorine and oxygen it is forming a compound with xenon? Because they are the most electronegative element which shows a compound which can form compounds with xenon. So, they form a number of compound with xenon, that is fluorine and oxygen can form number of compound with xenon, like some examples XeF2, XeF4, XeF6. And similarly, we have some compounds like XeOF4, XeO3. These compounds can be categorized into two types depending upon the elements involved in this compound. Here xenon and fluorine are involved. So such type of compounds are called as xenon fluorine compounds. that is the compounds made up of xenon and fluorine can be called as xenon-fluorine compounds. And the compounds in which xenon and oxygen are present, that type of compounds are called as xenon-oxygen compounds. Now let us discuss the preparation of xenon-fluorine compounds. Xenon-fluorine compound like XeF2, XeF4, XeF6. It can be prepared by the direct reaction of the elements under the appropriate experimental conditions. That is, here these compounds having only xenon and fluorine, so these can be prepared by direct reacting between these elements. But the important is that conditions should be taken appropriate. For example, XeF2 can be prepared, that is here it is shown in the ray diagram. XeF2 can be prepared when Xe and F2 is reacted when the ratio is taken in the 2:1 ratio. That means xenon is taken in excess and the temperature 673 Kelvin, 1 bar pressure. At the time we are getting XeF2. But if you want to prepare XeF4, again the reactants are the same reactant, but we have to take these in the that is in the 1:5 ratio. We have to take in the 1:5 ratio at the temperature 873 Kelvin and 7 bar pressure. At the time we'll be getting XeF4. But if you want to prepare XeF6, at the time we have to take same Xe and F2, but in the ratio that is 1:20 ratio we need to take. And the temperature 573 Kelvin, 60 to 70 bar pressure. At the time we'll be getting XeF6. So from this ray diagram it is clear that here the reactants are same, but we are getting the different product. That is, the conditions is taken appropriate in order to prepare the particle compound. So this is taking place in the extreme conditions because usually the xenon and fluorine does not combine in the normal condition. It only combines in the when the certain appropriate experimental conditions are given. In the normal condition it will not react because of the stable configuration of the xenon. So better we'll write these in the equation form in this way. So Xe plus F2 give rise to XeF2, Xe plus twice F2 give rise to XeF4, Xe plus thrice F2 give rise to XeF6. It's very simple to remember this equation. Only you need to change the stoichiometry here in the fluorine. Okay, here it is 1 fluorine, here it is 2 fluorine, 3 fluorine. And you'll be getting XeF2, XeF4, XeF6. It is very easy to remember this equation. XeF6 can also be prepared by the interaction of XeF4 and O2F2 at 143 Kelvin. So that means just now we have discussed one of the preparation of XeF6, but it can also be prepared, that is by the reaction between XeF4 with O2F2. So we are getting the product XeF6 plus O2. This is also reaction very easy to remember here, that is XeF4. So 1 fluorine, you have 2 fluorine that you can add here, so it will comes to XeF6 and 1 O2 will be remaining. So the equations actually in this group is quite simple. It is not at all difficult. So you can learn very easily these equations. Next, the properties of xenon-fluorine compounds. Xenon-fluorine compounds like XeF2, XeF4, XeF6 are the colorless crystalline solids and sublime readily at 298 Kelvin. They are the powerful fluorinating agent. That is important point. It's a powerful fluorinating agent. They readily hydrolyzed even by the traces of water. For example, XeF2 is hydrolyzed to give Xe, HF and O2. That is given in this equation. XeF2, which is hydrolyzed to give Xe, HF and O2. So, it is a powerful fluorinating agent. Xenon fluoride react with fluoride ion acceptors to form cationic species and fluoride ion donors to form fluoroanions. These equations are quite important equation. That is, this compound, when it react with the fluoride ion acceptor like F5 is a fluoride, this is fluoride ion acceptor, because when you look at this equation here, what is we are getting the product, that is a complex Pf6 negative. That is, in this product you can see one F negative is accepted. So Pf5 is accepting one F negative from XeF2. So we can say that Pf5 is a fluoride ion acceptor. So when the xenon fluoride react with the fluoride ion acceptor, that is Pf5 here. So what it result into cationic species. You can see the cationic species XeF plus, that is a cationic species is formed. How it is formed cationic species? When this xenon fluoride is reacting with the fluoride ion acceptor. Similarly, the next equation, in that also SbF5 is a fluoride ion acceptor. That is, one F negative from this, it is accepted by SbF5. So now SbF5 turns to SbF6 negative. And XeF4, because one F negative is given out, so it becomes XeF3 positive. That is, it forms a cationic species. So it is very important reaction, these two reaction. That is, these can, when it react with fluoride ion acceptor to form cationic species, but when it react with fluoride ion donors like MF is a metal fluoride like NaF, KF, RBF, CSF. So when it is react with a metal fluoride, at the time these metal fluorides are the donors actually here. They are the donors of F negative. So in this case here MF is donating the F negative to XeF6. So in that case, these can form the species, that is the fluoro ion species, that is a negative ion species is formed. So that is MF is giving rise to MF, that is giving rise to F negative to XeF6. So then XeF6 is turns into a negative species, that is XeF6 is already there and one F negative is accepted, so become XeF7 negative. So that result in the negative species. So these important are important, that is this equation and these equation are quite important. Next, preparation and properties of xenon oxygen compound, that is XeO3. XeO3 is the most important compound of xenon with oxygen, and we also have the compound like XeOF4, XeO2, F2. So these are the compounds in which xenon and oxygen are there. But in this compound, fluorine is also there. So the hydrolysis of XeF4 and XeF6 with water give rise to XeO3. So this is a preparation of XeO3, that is XeF4 with water give rise to XeO3, HF and O2. XeF6 with water give rise to XeO3HF. So by this method we can prepare XeO3 from XeF4 and XeF6 by the hydrolysis with water. XeO3 is a colorless explosive solid and has a pyramidal structure like this, which have a, here xenon have a sp3 hybridization. Let us discuss the properties. Hydrolysis, they readily hydrolyze even by the traces of water. For example, XeF2 with water give rise to XeHF and O2. But XeF4 with water give rise to XeO3HF and O2. But XeF6 with water give rise to XeO3 and HF. This is a 3 equation is very important reaction. Usually the question arises that is incomplete equation will be given. You have to complete, that is usual in the CBSE board examination. So here just do a comparative study here. Better to learn in this way. XeF2, XeF4, XeF6. Here we are doing hydrolysis, so we need to take water. When you compare the product here, what is a common product in all? Here, in this case, when you compare the first and second equation, xenon is the common product and O2 is the common, O2 and HF. These three are the common product, but here another product that is not is the first product, that is XeO3. So XeO3 we can prepare from XeF4. But when you look at the second and third equation, at the time which is a common product here, XeO3 and HF is the common product. So better to learn these three equations together, so you will not be having any confusion related to the products. So the balancing also you can check here. Next, structures. That is very important point here. That is the structures of these compounds. So first, let us discuss the structure of XeF2. The structure is linear. Now how it comes linear? So better will be use the method. We have already discussed Xe is the central atom and it have how many number of valence shell electrons? That is 8 valence shell electrons because of 18 group. So the number of electrons in the outermost shell is 8. Valence electron is 8. Now when you take this compound, that is XeF2, in XeF2 2 fluorines are there. So you make 2 fluorines. That is a 2 terminal. 1 electron you make a bond with fluorine. The one more electron you make bond with fluorine. Now count the number of electrons remaining as a lone pair. That is 1 here, 2 here, 3 here. So we can say there are 3 lone pair and there are 2 bond pair. How it comes 2 bond pair? Because it forming the 2 bonds here. So 2 bond pair and 3 lone pair. So what will be the sum? That is 5. So 5 means the geometry is trigonal bipyramid. So when it comes 5, so what will be having the geometry? That is trigonal bipyramid. This is the geometry. How we got the geometry? Because the total electron pair we got 5. So the geometry is trigonal bipyramid, as we have already discussed in the last video. Here the central atom is xenon, so we'll be keeping xenon in the center here. Now where need to keep the lone pairs? Because there are 3 lone pairs in that. So lone pairs always occupy a position where they experiences weak repulsion. That means where it experiences very less repulsion. So this is the most appropriate position. And so now what is remaining? 2 fluorine are remaining. So here is 1 fluorine, here is 1 fluorine. So when you compare the structure here without the lone pair, when you consider it having a linear structure. So it's linear shape. So its shape is linear, but the geometry is trigonal bipyramid. So this is what actually the structure of XeF2, that is linear structure, but geometry is trigonal bipyramid. Next, XeF4. XeF4, here the central atom is xenon. How much electrons are there? 8 electrons are there. 4 fluorines are there. Terminal atom 4 fluorine. So we need to make the bond like 1 electron with 1 fluorine. This is the second, third, 4. So these much of electrons are utilized in making the bonding. So how much lone pairs are here? This is 1 lone pair. This is 1 lone pair. So we have 2 lone pair and there are 4 bond pairs. So total is equal to 6. That is 4 bond pair and 2 lone pairs. So 6 means what is the geometry? 6 means the geometry is octahedral geometry. So we'll be making octahedral geometry. This is the octahedral geometry. 6 tips are there. You can see we got the total electron pair 6 tips, that is octahedral geometry. Now keep the central atom in the center, that is xenon. Here we need to keep the lone pair because when there is an octahedral geometry, at the time the lone pair should be kept on the axial position, that is one is above the plane, other one is below the plane. So the rest of the position will be having the 4 fluorine. So this is the geometry, that is octahedral geometry for the molecule XeF4. But shape, when you are considering the shape at the time, we have to avoid the lone pair. So better we will rub the lone pair here. When we are talking about the shape, just remove the lone pair. So just I will rub it out here. Now look at the structure. What is the shape here now? It is a square planar structure. Why it is planar? Because all the fluorine, that is 4 fluorine and the xenon, all are in the same plane and it is occupying the 4 corners of a square. That's why it is a square planar shape. Next, XeF6. In this, the central atom is Xe. So we'll be making Xe in the center, and here the electrons, total 8 electrons are there in the valence shell. That is a 8 electron. 6 fluorines are there in this compound. So we'll be writing 6 fluorine here. This is 2, 3, 4, 5, 6 fluorines. We need to make 6 fluorine. These 6 electrons, that is out of 8, 6 electrons will be used in making the bond. It makes bond with 6 fluorine in this way. So tell me how much is remaining here. That is out of 8, 6 is used in forming the bond with the 6 fluorine. So 1 electron pair is remaining. That is called as a lone pair. So here how many bond pairs are there? 6 bond pair and 1 lone pair is, that is the total is equal to 7. So 7 is actually pentagonal bipyramid, but these, instead of having pentagonal bipyramid, these have a geometry that is called as distorted octahedral geometry. That is, it is in the form of octahedral. That is, this is the octahedral we already familiar. This is the octahedral. So 6 fluorine and 1 lone pair. So that lone pair will be here, it will be there. So the geometry of octahedral will be get distorted because of this lone pair. So we can say that its a geometry is distorted octahedral geometry. Why it is distorted? Because of the presence of one lone pair here. So the geometry is distorted octahedral. Next, that is XeOF4. So here which one is the central atom here? Here also the central atom is Xe. Make the 8 electrons in this way. Here 4 fluorine and 1 oxygen is there. So 4 fluorine. So let us make 4 fluorine here. That is F. So we need to make 4 fluorine and there is a 1 oxygen, single oxygen. So that I also make it here. So terminal atoms here, 4 fluorine and 1 oxygen is the terminal atom. Now how to make the bond here? So 1 electron it will be shared with fluorine, each fluorine. So like this, total 4 electron is utilized in making bond with 4 fluorine. But oxygen, it can form, you know that oxygen have 6 electrons in its valence shell. So it requires 2 electrons in order to get stabilized. So here the 2 bonds are formed between the xenon and with oxygen. That is important here. Oxygen with the xenon, it is forming the double bond here. And 1, so here 1 lone pair. Now tell me how much will be the bond pair here. So let us count the bond pair here. 1, 2, 3, 4. 4 bond pair with fluorine. But oxygen 2 bonds are there. But according to VSPR theory, the multiple bonds should be taken as considered as single. So this double bond taken as single. So total how many bonds are there? Once again just count it. 1, 2, 3, 4 and this is 5. So total 5 bond pair, as multiple bonds should be considered as single according to VSPR theory, and plus 1 lone pair. So total that is equal to 6. So 6 means the geometry is octahedral geometry. So when we are making an octahedral geometry, xenon is in the center and 4 fluorine and 1 oxygen is there, and 1 double bonded oxygen and 1 lone pair. So we can, how we will arrange these? That is 4 fluorine that is occupying this position, that is a square planar position it occupies, but the 1 double bond O is that double bond O will occupy this position, that is above the plane, and 1 lone pair is there, that is occupy the below the plane. So this is the geometry, that is octahedral geometry. But when you are considering the shape, when you are finding out the shape at the time, you have to avoid the lone pair. So when you avoid the lone pair, that is better, I will rub it out. So when you avoid the lone pair, now what is the geometry? The geometry is a octahedral, but the shape is square pyramidal. How it comes square pyramid? When you look at here, it look like a pyramid. It is a square pyramid. So this is the geometry, that is octahedral geometry for a XeOF4, but the shape is, that is square pyramidal. Next, XeO3. This is also will be doing in this way, that is first we will be making the xenon 1, 2, 3, 4, 5, 6, 7, 8. And here 3 oxygens are there, and I told you oxygen, it forms double bond, that is double bond O here, double bond O here, and the electrons are used here, double bond O. So tell me how much electrons are remaining here? There is a 1 lone pair. And how many bond pairs are there? 3 bond pair, because double bond should be taken as considered as single. So here there is single, here there is single. So total 3 bond pair and 1 lone pair. So that is equal to 4. So 4 means what will be the geometry? That is tetrahedral geometry. Tetrahedral geometry, how we make tetrahedral geometry? This is tetrahedral geometry. From this 3 oxygens are there. So that oxygen we will make in this way double bond O, 3 oxygen, double bond O. And there is one lone pair. So one of the position is occupied by the lone pair. So the hybridization is sp3 here, and the geometry is, that is tetrahedral geometry. But the shape, for the shape we have to neglect the lone pair. So better rub it out the lone pair. When you rub it out the lone pair, now you can look at here what is the shape now. Now it is like a pyramid. You can see now this is like a pyramid. So geometry is tetrahedral, but the shape is pyramidal. So this is very important to learn the structure of compounds of xenon, because usually you will be getting question on this area. That is, what is the structure for XeO3? That is, structure is tetrahedral, geometry is tetrahedral, but the shape is pyramidal. XeOF4, that is shape is square pyramidal. XeF6, that is distorted octahedral. XeF4, that is square planar, and XeF2, that is linear shape. So this is what we have discussed about the structure of important compounds of xenon. So this is all about this video, that is the discussion we have done for the compound of xenon with fluorine and oxygen, and we also discussed the important physical and chemical properties here. So this is all about this video. Have a nice day.